and gentlemen, the books is in. The books are in. Yep. They're in. They're here.
Log in to KofiPaisaTV.com and get Spears of the Mossy Volume 1 by Kofi Paisa Research Team, from Spears the Pen Volume 2 by Kofi Paisa Research Team, Spiritual Combat Volume 3 by Kofi Paisa Research Team, One Night Before Bed by Any Harret Shawn Calfunny, Kalawa's Trip to the Motherland by Kofi Paisa, From Cocaine to Consciousness by Any Harret Shawn Calfunny, As I Learn, We All Learn by Kofi Paisa. Also, if you want fresh merch, go to our online store, Family Connect Apparel, and get all the brands. Also, get our 54 deck of quiz and educational cards available now on KofiPaisaTV.com.
ETM Hotel, Rennie Shawn, welcome in peace. This is your brother Shawn. I'd like to thank everybody for tuning in to Science with Shawn this evening. Happy Father's Day to all the fathers, to all the mothers who have assumed the role of playing both. This is still not your day, but we will recognize your efforts and congratulate you on stepping up and being the head of household and holding down the males and female children that you have given birth to. And we apologize for all the deadbeats out there in the world. However, like the show, share the show, tell a friend, tell a friend. Let's have a nice little build this evening and see if we can learn something together. So there's a lot of, I don't want to call it rhetoric, but there's a lot of talk on social media about natural infection and not getting the vaccine, and already having been infected and don't see a need for the vaccine. And that's what this evening is about, addressing the best way that I can address it, that conversation. More importantly, how your immune system works, right? To a degree. We'll speak a little bit about the innate and the adaptive, because I think that's the disconnect in the conversation, is people don't understand the difference between innate and adaptive. And people think the adaptive is a solution to a much bigger issue. So again, I am streaming from the Mossy Warrior Clan YouTube channel and Science with Shawn. I am trying to big up the Science with Shawn channel, which we are on right now. So for those of you who have not subscribed to Science with Shawn, I'm gonna drop the link again in the Mossy Warrior Clan chat. And for those of you who are tuned into the Mossy Warrior Clan YouTube channel, please join us on the Science with Shawn. Let me go ahead and say peace to Nunu, Tika, Mika, Robert Rand, Taarka, Donnie from West Africa, Omar, Brother Charles. You already know, I know Pure Black is going to show up unless some pseudo going on and he trying to catch it. Peace, Sister Bonita. You know what I'm saying? I don't know who else may join. I don't know if any of the brothers from the teams are joining this evening or not. You know, I just was impromptu, so I decided to want to have this conversation on the front line. So again, the motivation behind this is a conversation that I was having pretty much with a bunch of people. But of course, if you know, you go on Unc West's Facebook page, you're going to catch tons of Facebook scientists engaged in a conversation that's unrelated to the actual topic. And in those conversations, there's a lot of people that are talking about natural immunity versus vaccine immunity, but which one's better, right? We all know, I can't say we all know. We all should have some type of command and understanding for the differences between the two. Again, everybody that's on the Mossy, that's tuned in right now, we are on Science with Shawn YouTube channel, and I did drop the link in the chat. So if you are on the Mossy, which still has some viewers, just hit the little YouTube link right there, man, and join us on the Science with Shawn channel. Subscribe to the show. Subscribe to the channel. Peace, Teddy. Zane, what up? Again, like the show, share the show. Tell a friend. We live. And we're going to have a nice little conversation. So before I get started, as always, and I'm just waiting on a few more people to come in the building. I did see a jump. What up, Rob Rich? Again, we are on Science with Shawn. And I'm going to end the Masa Warrior Clan soon, but I want to go ahead and put this disclaimer on the screen because I am going to show a video. So copyright disclaimer under Section 107 of the Copyright Act 1976. Allowance is made for fair use for purposes such as criticism, comment, news reporting, teaching, scholarship, education, and research. Fair use is a use permitted by copyright statute that might otherwise be infringing. So again, yeah, man, join us on the Science with Shawn's YouTube because I am going to shut down the Mossy. So if you're on the Mossy, what up, Rob Rich again? If you're on the Mossy, everybody that's tuned into the Mossy, I just put the link to the show in the chat. All right. What up, James? What's good? This vaccine is legitimately hurting people. Natural immunity all the way. Appreciate that, Brother James. Can you hit this link right here that I just dropped, man, and join us on the Science with Shawn YouTube channel? Natural immunity can kill you. I'll tell you that right now. I ain't even got to get into the conversation, but if you think a natural immunity has already wiped away 3+ million people and has damaged the lives of millions more, which we're seeing going long COVID. Maybe I just need to leave the Mossy up for a little bit. But we are on the Science with Shawn YouTube channel. Please hit the link if you're in the Mossy. Hit the link and join us on the Science with Shawn YouTube channel. And well, I'm gonna try to drag this out. So again, today's topic is about natural immunity versus vaccine immunity. The conversation started from a Facebook post stemming from people who seem to think that, think that. And I'm gonna put his comment up so y'all don't, because he's on the Mossy for those on the Science with Shawn. So there's his comment right there, right? We see his comment. So we got one person that came in and immediately said the vaccines is legitimately hurting people. That is a claim, right? That is a claim that has not been proven. For someone to say that the vaccines are hurting people, the vaccine, what up, T? Where's the evidence for that, right? So we saw the claim. We're going to address it. And we're going to deal with it. So again, I want everybody to join us on Science with Shawn YouTube channel. I'm streaming from both the Mossy and the Science with Shawn YouTube channel for a reason. Because I know a lot of people will miss it and are unfamiliar with the fact that we do have a Science with Shawn YouTube channel based on some things. So before I get started, please like the show, share the show, tell a friend, tell a friend. We're gonna get it in. We're gonna go from there. So hold on real quick. Never mind. All right. So again, I already read the Copyright Act. I'm gonna share my screen again. Let's learn. Let's see what we can learn today. So again, I just want to go through something that I dealt with on Dr. Ma's channel, right? Everybody familiar with the conversation I had with Keita Wadu and how he, the naturalist, proposed. Hold on, let me make my screen bigger. He proposed an alternative, right? So when he proposed the alternative, he really didn't have a solution. He just proposed an alternative way of trying to treat an infection. So you would have to be infected in order for his alternative to even be administered. So in that conversation, we talked about the immune system briefly. All right. So I just want to bring this back up so we can move forward. So the immune system is the body's defense system against an infection. Humans possess 3 types of immunity. We have innate, which you're born with, adaptive, which you develop over time, and passive, which is borrowed, right? So an example of passive immunity would be like a newborn baby, collecting or having some type of antibody response to COVID-19, right? Because you see the antibodies showing up in the placenta after birth of the pregnant women who have received the vaccine or who have been infected with COVID-19 and developed some sense of antibodies. Now, the child is to get vaccinated or advised to get vaccinated. Why? Because passive immunity, the antibodies worn pretty quickly. They wear off and they don't exist over a lifetime. So it's best to vaccinate a child who receives passive immunity. Then you have adaptive immunity, right? Adaptive, you have to adapt. It's exactly what it is. And we're going to get into that more specifically in this conversation. And then, of course, innate, it's what you're born with, and, these 3 types of immunity make up your immune system. Now, the immune system takes a while to develop immunity, and that is why vaccines have helped. All right, so I'm gonna read from my virology book, right? Principles of Virology, the 5th edition. This will be volume 2, which deals with pathogenesis and control. And then I'm gonna get back into the slides. So it says that let me get to the nitty gritty, right? So it says the innate immune response is crucial in antiviral defense, but it can because it can be activated quickly, functioning within minutes to hours of infection. Such rapid action contrasts with the activation of the adaptive response, which is far slower than the infectious cycle of most viruses. It takes days to weeks to orchestrate the effective response of antibodies and activated lymphocytes specifically tailored to the infecting virus. So while the speed and potency of innate immunity is important, this response must also be transient because its continued activity is damaging to the host. So in short, the innate works faster, it's quicker, right? And it gives you a better response because the adaptive takes time, right? This is why they say antibodies don't develop as soon as you're infected. It takes a while for you to build up the antibodies naturally. So if you're naturally infected, it's, this is why you see it take that process. Now, we're going to get more into specifics of how long that process is, and we'll deal with it in general. And I hope, Brother James, if you're still with us, I hope that you're still around for the rest of this conversation. Yep. Rob Rich, I'm looking in the Massa. Rob Rich says, hey, bro, Sai have COVID-19. I know because his symptoms are similar to mine. He's just going to get worse. He needs to make sure he doesn't have pneumonia in his lungs, or it's going to get bad for him, for real. Yep. Peace of coma. How you doing? Yep. So yeah, again, everybody that's on the Massa, we are streaming from the Mossy and the Science with Shawn YouTube channel. I'm gonna put the Science with Shawn YouTube channel again if y'all want to join everybody that's on in the Science with Shawn chat room that is communicating as well. And Pure Black said that James, that you just made that up. So I don't know if you're still around, but you got some people on your head. Now, let's get into this. All right, so here we go again with the immune system. The source, of course, is National Institute of Health. It says the immune system is made up of special organs, cells, and chemicals that fight infections, microbes. The main parts of the immune system are white blood cells, antibodies, the complement system, the lymphatic system, which you heard me mention, lymph nodes, the spleen, and the thymus and bone marrow. Now, in a recent publication published in the Journal of Nature, you heard about them looking for antibodies in the bone marrow to develop into being a T cell situation where they were stimulating. And in that research, they came to a conclusion of how long the antibodies last, or how long that memory. Remember this word, immune memory. That's a key word that I think you may hear in an up and coming publication. And you'll find out more about that later. All right, so your immune system works to root out germs and other invaders that have no business in your body. For example, if you inhale a cold virus through your nose, your immune system targets that virus and either stops it in the tracks or primes you to recover. It takes time to get over an infection, and sometimes you need medicine to help. But the immune system is the cornerstone of prevention and recovery. So I think people need to fully understand that. Remember, we inhale 6 liters of viruses every time that we take a breath, right? Every time that we really take a breath, we're taking in 6 liters of viruses coming into our body. So these are some ways, of course, you can strengthen the immune system, which would be rest, eating healthy, dietary products, exercising daily, being sanitary, are ways that actually help not boost, that's a bad word, strengthen the immune system. Now, your immune system can also be weakened, right? Alcohol, smoking, poor nutrition, AIDS, HIV, those things can affect the immune system. This is one of the key pieces of why they did a trial with people who had HIV. They did the COVID testing on them. They had a small portion of people that tested who were HIV positive, and those people were part of the trials, and they were looking to see if they could develop any type of antibodies. Why? Because with HIV, it attacks the things that make you healthy immediately. So that we got that data from there, and we can kind of move on. All right, you hear this word all the time, herd immunity. I'm not going to get too much or too far into the herd immunity thing, because there's a target threshold for the amount of people we need to vaccinate in order to achieve herd immunity. Herd immunity can't be achieved without a vaccine. Natural infection, I'm telling you right now, natural infection can lead to basically the virus mutating in one's body. And then when it is passed to somebody else, this is how you get a different variant, right? So we need to understand that adaptation, mutation process with these variants, because we can get naturally infected. It can mutate in our body and it can go forward. If you do not believe me, I will pull up a study regarding a lady who had, I think she had HIV. She was infected with COVID and it mutated 30 times just in her body alone. I'll source that up for y'all real quick. So I just don't want y'all to think that I'm just talking. Again, everybody, I am streaming live from the Mossy and Science with Shawn. I am dropping the link. Well, I just dropped the link in the Mossy Warrior Clan chat for people who want to join everybody that's on the Science with Shawn in the chat and be a part of the discussion. Just bear with me a minute. I'm about to appreciate that, Infinite Minds. I know you in the building because you just tagged me in the post. And we're gonna go from there. But let me pull up this study for y'all real quick. Of course, y'all know I gotta go to my vault, right? Gotta go to my vault and get that source for y'all. But yeah, please like the show and share the show. We can have some fun learning today. Yeah, and they popping firecrackers where I'm at. Yep, they've been doing it the last few days. But I guess it's firecracker popping time. All right, so I see the session just went live. All right, go ahead, Woo. I almost got my source where I need to be so I can pull it up for y'all. All right, so hold on one moment for me. I'm gonna end that part of those slides so we got a clear understanding of what the three most important parts of the immune system are: innate, adaptive, and passive. All right, we know innate is what we want. We know adaptive takes a while, and we know passive wears out. You know, we know how to get passive, right? We spoke about that, so everybody should be familiar with that. Now, the immune system does get more technical than that, and you know, I don't want to get as technical, right? Neither does your hairline. Your hairline don't know what it's talking about. All right, so I hate when this do this. All right, so y'all should be able to see this on the screen pretty clearly. All right, so right here, we have persistent SARS-CoV-2 infection and intrahost evolution in association with advanced HIV infection. We have the authors of the study right here, the journal right here, submitted and available on CRISP website 2021. The abstract is right here. The full PDF text download is here, and we'll get into that in just a second. So while most people affected with SARS-CoV-2, there are several reports of prolonged infection in immune-suppressed individuals. Here we present a case of a prolonged infection of greater than 6 months with shedding of high titer SARS-CoV-2 in an individual with advanced HIV and antiretroviral treatment failure. Through whole genome sequencing at multiple time points, we demonstrate the early emergence of the E484K substitution associated with escape from neutralizing antibodies, followed by other escape mutations and N501Y substitution found in most variants of concern. This provides support to the hypothesis of intra-host evolution as one mechanism for the emergence of SARS-CoV-2 variants with immune evasion properties. All right, so for people that's unfamiliar, let's go. All right, so okay, you should be able to see my screen a little bit. Let me zoom in more. There we go. Can you see it? Let me check YouTube. All right, so yeah, people should be able to see that a little bit. Let me zoom in a little bit more. A little bit more. There you go. So I think that should be good for people with bad eyes. I hope it's not blurry. Is it blurry? I hope it's not blurry. It might be blurry on people's cell phones, but if you're on like an iPad or a laptop, it's not blurry. Mongo said this sound like he letting things off on his end. All right, so persistent SARS-CoV-2 infection and intra-host evolution in the association with advanced HIV infection. Okay, this is the study right here. All right, now all my sources, description to all my sources are in the chat except for this, and I'm gonna drop this. I'm gonna drop this in the chat for y'all in case anybody interested in wanting to know more. But here you're going to see these are the two, right? The two most important things is recognizing these different type of variants and stuff. So I've already read this pretty much, this first little part. So here's the introduction. Coronavirus disease 2019 is an acute respiratory illness caused by severe acute respiratory syndrome related coronavirus 2. While most people effectively clear SARS-CoV-2 infection, there are now several reports of prolonged infection associated with underlying immunosuppression. In many of these cases, there has been evidence of intra-host evolution characterized by the emergence of viruses with mutations in the spike glycoprotein. It has been hypothesized that intra-host evolution can be one mechanism of the emergence of SARS-CoV-2 variants. Here we describe a case of prolonged SARS-CoV-2 infection in a person with advanced with HIV and antiviral treatment failure without either clinically induced immune suppression or neutralizing antibody-based treatment of SARS-CoV-2 infection and present analysis of the virus evolution over time. So here's your case report. 36-year-old female was admitted to the hospital on 2020 with sore throat, cough, and dyspnea. Now, I always mess that up. I can't say it. Symptom onset 12 days of admission. She had been on HIV antiviral therapy since 2006. Most recently, a fixed dose combination of tenofovir. Now, this is a big one. Emtricitabine and ephedrins. Now, other relevant medical history included a single episode of tuberculosis in 2006, with chronic asthma for which she received inhaled budesonide and salbutamol. On the day of admission, day 0, SARS-CoV-2 reverse polymerase chain reaction, or RT-PCR, of a nasal vaginal swab specimen was positive. All right, so she tested positive. Okay, and she was managed in a general COVID-19 ward, received oxygen via face mask and 6-day course of dexamethasone, and was discharged at home after 9 days. During her hospital admission, she was enrolled in a prospective cohort study exploring the effect of HIV on the natural history of immune response to SARS-CoV-2. She was reviewed at enrollment, day 6 of admission, and day 16 post-symptom onset, when she was placed on non-high flow supplemental oxygen, and in the clinic on day 20 and 34, she was asymptomatic. On day 71, she complained of chest tightness. Oxygen saturation was documented to drop to 96 to 76 exertion. Chest x-ray showed non-specific perihelia infiltrates. She was treated empirically with pneumonitis, Jirovecii pneumonia of ambulatory basis, 21 days of coltrexazole and prednisone. Now, she was reviewed on day 106, right, when she had fatigue, and day 190 when she was asymptomatic. Now, on day 190, antiviral therapy was switched to a fixed dose combination of tenofovir, which they gave some more medicine, And on day 206, she achieved HIV viral load suppression. All right, now that was a lot, but that was, basically what happened. Now they have their methods here, which I'm not going to bore you with that. We had pretty much got that. Now, here's where it got interesting. SARS-CoV-2 whole genome sequencing. 6 specimens collected as part of a cohort study, days 6 through 190, and the residual nasopharyngeal swab specimen collected from the routine diagnosis on day 0, processed, right, by the KwaZulu-Natal Research Innovation and Sequencing Platform Laboratory, CRISP. Okay, they extracted SARS-CoV-2 RNA using the viral DNA kit for automatic Magic 360 system. Converted the RNA to cDNA using the superscript 4 first strand synthesis system. Performed the SARS-CoV-2 whole genome amplification by PCR using primers designed as primal scheme, generating 400 BP amplicons with an overlap. So they just basically did a whole bunch of testing on her, swabbing and collecting samples. All right, so they got all the samples that they need right here. This is all this is saying. This is sample generating, and basically sequencing has begun. Now, as you can see, the genomes in the study were analyzed against a global reference data set of 3,566 genomes, including 486 genomes from South Africa using a custom build of the SARS-CoV-2 next strand. Yeah, I remember we've been in next strand before, right? The workflow performs alignment of genomes, phylogenetic tree interference, tree dating, and ancestral state construction and annotation. And the phylogenetic tree was visualized using the ggplot and the ggtree. In addition, resulting time scale of phylogeny can be viewed interactively. All right. Now, of course, they're using next strand. We've been in next strand. We ain't got to do that. We ain't got to go there. So we know they did it. They did PCR testing from day 0 to day 190, but in this instance, day 216. All right, during that range, right? They had a range of 16.4 to 31.6, which they revealed in the table. They detected certain things at certain points in each testing. And every time they went up, she had some new symptoms. So every time she complained about a new onset of something, they test her, and then they checked her out for other things. All right. So the scary part of this whole story is that the virus at each stage in each phase of the testing, in summary, was mutating, right? It was mutating, and they were trying to sequence the mutations and match them to the potentials of what they were seeing in the public with all the other variants that were out there. So this lady with HIV, this 36-year-old lady, got COVID-19, complained about symptoms on such and such days, and every time the virus was in her, would attack her, chill out, attack her again, chill out, attack her again, chill out, attack her again, and chill out for a span of about 6 months. When her symptoms would subside, it would come back. So, yeah, that's pretty much what all this is. And as you can see, you'll see E4A4 mutation, F490OS mutation, D614G mutation. You see all these different mutations that were going on? All genomes fell within Pango lineage. So I don't want anyone to think that I'm just making it up. It's saying it right here on the screen, and I'm telling you straight up without having to read all of this to you. All genomes fell within Pango lineages B11273, a South African lineage. All right, from previous part B1156, one of the most prevalent. First wave epidemic prevalent. And look, the sequence at day 0 had D614G. It mutated. Then it goes to G142V, D796Y at day 6, and E484K. substitution receptor binding RBD emerged alongside the substitution of S subunit. And then the E4A4K mutation remained consensus sequence until day 34. After day 34, bloop, 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 we get day 35 to the 71, we get the K417T and the F490S mutations. It just kept on. Look at it. Followed by the emergence of L455F and 4F56L at day 106. And of course, this diagram to the left is next strand, as you can see. And then it goes on to explain the sequencing below the phylogenetic analysis of 7 SARS-CoV whole genome sequences, right? So this lady with HIV was having a mutation problem in her body with this virus, COVID-19. All right, so like I said, I don't want to spend a lot of time here. Just to give you all the gist of it, I didn't want to just bring it up and not be able to provide you with a credible source, okay? Because that ain't how I roll. Now, I'm going to put the study in the chat, and then we will proceed. Who doing what now? What up, Keenan? Sister Safa, what's good? Again, y'all, I am streaming from both the Mossy and the Science with Shawn YouTube channel. Anybody want to join? There go the link. Now I put the link to the Science with Shawn in one chat, and I put the link to the source that I just put on the screen in both chats. All right, so I'm going to reshare again, and we're going to get into the whole argument of natural immunity versus vaccine immunity. All right, we'll continue on with this. Okay, boom. All right, so I want to bring forth to everybody a few sources here, and each of these sources are in the description. This one's from GoodRx. Okay, this is written by we can see her right here. She is a pharmacist editor for GoodRx. She's earned a doctor of pharmacy from Wilkes University in Wilkes-Barre, Pennsylvania, licensed in Massachusetts and Pennsylvania. So this is Mrs. I guess you say her name is Angst. All right. Now, she published this on 5/13/2021, so it's updated. Now, she did give us a few key point of takeaways, so we don't have to go too far in the article, but we are going to make our argument. Okay. People who were sick with COVID-19 and recovered might have long-term immunity that lasts for months or years. Now, there's some stuff going around talking about long-lasting immunity. Brother Chabe is in the chat right now, but Brother Jay Boudon, he kept on mentioning long-lasting immunity. And I kept on saying, well, how long does immunity last when we have documentation that the antibodies worn off between in the first 4 months? Well, after month 4, the antibodies dwindle. Between months 4 and 7, you lose a lot of your antibodies. By month 11, you have some recognizable antibodies in the body, but not enough. And if you know anything about once you lose your antibodies, it makes you susceptible to reinfection. So she says that's point number 1. And I think this word right here, long-term immunity, is misinterpreted by Facebook scientists and people who don't really study the subject matter extensively or on a day-to-day, as most other people do. Most of us do. All right. Now, we don't know how long the vaccine immunity lasts yet, but it's much safer to gain immunity from the vaccine from getting COVID. Experts believe the vaccine will still work against new strands from the UK, South Africa, but antibody treatments might not. So let's see what she says here. All right, now immunity is a word used to describe how your immune system makes antibodies to protect us from infection. Making antibodies to a bacteria or virus is a process our bodies undergo, naturally after we've been sick. So we got to get sick first for our body to naturally create a defense mechanism. I want you to think about that. Your body, you have to get sick first in order for you to create some type of defense against something. In you becoming sick, you put yourself in position to do a numerous amounts of things. You risk your health, right? COVID tongue, COVID lungs, COVID heart, COVID kidneys, COVID toes, COVID fingers, brain fog, loss of smell, taste and smell, loss of memory, a ravaged heart, the potential threat of needing a double lung transplant, which have increased, potential risk of reinfection, and the reinfection cases have not, there's not enough data on reinfections. So let's be honest right now, reinfections have not been properly studied. So for people who think that, oh, you can be reinfected, they haven't really done the work on that. They think it may be possible. There's a small portion of the population that can catch these reinfection cases. We had people who caught it 3 times, people who caught it twice. We got people who still having troubles in part of cohort studies right now that we're waiting on publications. But those are some of the things. All right, so continuing on. But one of the best ways we can create immunity is through vaccines. A vaccine teaches our immune system to fight an infection without actually making us sick. So in the first paragraph of this article, this argument that we're having right now is natural immunity versus vaccine immunity. And in the first paragraph, she closes by saying a vaccine teaches our immune system to fight an infection without actually making us sick. Whereas natural immunity, we have to get sick in order to create a defense. You see the difference? So that draws the line in the sand right now. Now, I don't need to read all of this for people to fully understand that that's the difference between natural immunity and vaccine immunity. The vaccine is much safer. It doesn't have to do all the things that natural immunity does to protect us. Now, not all vaccines are equal in how long their protection lasts. Some vaccines, like MMR, will provide lifelong immunity once you get both shots. Others include the flu shot, require you to get vaccinated every year. And some, like the tetanus, right? Or somehow somewhere in the middle, requiring boosters after a certain number of years. Now that vaccines for COVID-19 are being administered across the country, people are now wondering how long does immunity last from the vaccine. And we should expect to receive a COVID-19 shot every year from now on. However, I dropped an article. I don't think that I put it on Facebook. I didn't, but I shared an article talking about we might not even need a booster shot based on some recent information, some recent data that has been published. Now, I was sitting on that because I felt like that I may get into an argument with somebody. And if I did get into an argument with that somebody, appreciate that, Keenan. Happy Father's Day to you too. If you're a father, bro. But yeah, let me see if I can get that. Let me see if I can find it for y'all, because I might have to put that on the screen. Might. Let me go to Mossy. Put the money in there. All right, let me see. Did I put it in this one, Chavis? Yeah, so Nah, I put the brain stuff in here, but I get it, man. Oh yeah, it says don't count on needing a COVID booster shot. This is from WHO scientists. The article was published in Bloomberg, and it says we do not have the information that's necessary to make recommendations on whether or not a booster will be needed. This is from Swaminathan, Somaya Swaminathan of the World Health Organization. She is the chief scientist. She said it in a Zoom chat on Friday. The science is still evolving. She's saying it's a premature call for people running around basically saying a booster shot would be needed. So all this COVID booster shot hype is just rhetoric at this juncture. We need to let the science speak. All right. So that's pretty much what she basically said. Now, I am going to do everybody a solid, and I'm going to post that link in the chats, right? Because, you know, around here, we got to do two things. We got to source up, or we got to shut up. So I got that in both. All right, so let's continue our bill. One moment here. Now, so how long does it take to develop immunity to COVID-19? It's one of the questions. How long does it take to develop immunity to COVID-19? There are two different ways your immune system can learn to make long-lasting antibodies for a virus or a bacteria: natural immunity and vaccine-induced. Natural immunity is when you make antibodies after you recovered from an infection. Vaccine-induced immunity is when you make antibodies after you receive the vaccine. So again, this is about natural versus vaccine-induced immunity. There again, we have a clear distinction. I have to be infected first, and then I have to go through sickness in order to develop some type of antibodies with natural immunity, risking my health, the threat of risking my health and my livelihood because I'm out of commission. What if I get sick? What if I'm asymptomatic and I just have some minor stuff? I still gotta what? I still gotta quarantine. So that means I can't do too much of anything, right? I'm slowed down. I'm hampered. I'm fighting certain parts of the, well, where Rob at? Rich Rob had it, right? Now, he wasn't on no deathbed. He was at home, but he was going through a whole phase. But he couldn't get up and do the things that he wanted to do, and his was worse. And then over time, he began to feel a little bit better. But that was a natural infection. And then he didn't even have any antibodies during that gap because he was still going through it. It takes too much time to develop some type of antibodies with natural infection. Vaccine induced, you on the spot, you on the go. It's much quicker, we moving. Now, both are effective ways to develop immunity. However, vaccine-induced immunity allows your immune system to learn how to protect you without actually getting sick. There's a lot we're still learning about the novel coronavirus, but here's what we know. All right, so here's the argument. Natural immunity says if you get sick, COVID-19, your immune system will make antibodies within a few weeks after you're infected. However, this does not mean you will feel 100% better. Many people are experiencing long-term effects for weeks or months after infection. Natural immunity means that once you have developed immunity, your body will know how to fight the infection if you are exposed again. Reinfection is possible, but unlikely. Vaccine-induced. It takes a couple of weeks for your body to build immunity after vaccination. For that reason, you are not fully protected until 2 weeks after your shots. This means 2 weeks after getting your second shot of the Pfizer, BioNTech, or Moderna, and 2 weeks after Johnson & Johnson's single shot. Regardless of which vaccine you get, though, there are two important things to remember. It's necessary to get both shots of the two-dose vaccines to be fully protected. It's still possible to get sick with COVID-19 right after being vaccinated because you can be in between those shots. And we all know that you can get infected today, a vaccine tomorrow, and symptoms show up a few days later, and it can work that way. Or you can get your vaccine today, and in between that, building the immune system or training the immune system or building those antibodies up, you can get infected. So we know that, right? All right. So how long does natural immunity last for COVID-19 infections? Remember I said this word right here. Immune, well, I didn't say immunological, but I said immune memory, right? So immunological memory, all right, is the technical term for immunity. There are 3 types of white blood cells that help our immune systems to protect us. Remember in the presentation, in the slide, I said something about white blood cells. Now you have macrophages, B lymph nodes, and T lymphocytes. Lymphocytes and T lymphocytes, right? Remember that. You got your B cells, T cells. We're just breaking them down like that. Now, macrophages are these cells will attack and break apart the virus and bacteria when we are sick or shortly after we receive the vaccine. What they leave behind when they're done are known as antigens. B lymphocytes these cells are known as the B cells, make antibodies to attack the antigens the macrophages left behind. The antibodies are unique for that particular virus or bacteria. If the same infection gets into your body again, your B cells will make these unique antibodies and kill the infection right away. T lymphocytes. These cells, known as T cells, are responsible for taking care of the cells that have already been infected by the virus or bacteria. They will kill these damaged cells and the infection inside of them. These cells are also responsible for remembering each and every virus and bacteria you come into contact with for the rest of your life. All right. That makes that study with nature very important to know because we learned that natural infection, the antibodies begin to fade and you begin to lose them, making you susceptible. All right. I'm not going to go too far on this, but we kind of laid the groundwork for a natural versus vaccine. Now, let's get to it.
Hi, I'm Marty McCary with MedPage Today. I have the privilege of being here today with Dr. Raccaniello from Columbia University, a professor of virology. Vincent, great to be with you. Thanks for joining us.
Thank you for having me.
When you get together with other virologists, people that you respect in your field, what are you talking about? What concerns you guys? What are you thinking about? Are you optimistic?
Well, it depends, when in this outbreak, at the beginning, we didn't know if we would have vaccines. So we're trying to understand how the virus spread and how we could get around it. And now that we do have vaccines, the narrative is completely focused on vaccines. And then, of course, the variant story emerged in January, essentially. And we've been talking a lot about how the variants are going to behave in the face of vaccination. And most recently, we've brought up the T cell story that I mentioned earlier and how this was largely ignored. And it turns out that they may end up saving us. So I would say in the last few weeks, it's all about vaccination. Now, of course, we see side effects or associated effects with some vaccines. We talk a lot about that. I must say that early in the outbreak last year, when the vaccine development was just ramping up, we talked a lot about this idea that should they really only be focusing on spike? Shouldn't they be putting some other viral proteins on? And, in retrospect, it was a good decision to get vaccines out in less than a year because otherwise it might have been more complicated. But that's partly why all the variant arising now, because we have only the spike epitopes in there, and so it's easy for the virus to get around that. So it's two ways, that story. So those are the things that we've talked about, and also I should say we talked a long time about antivirals and whether they would play a role. And we looked at remdesivir and how it was given so late in infection, and we said, this is not going to work. It's too late. That's an inflammatory disease later in infection. And it turned out remdesivir, yes, doesn't work if you give it in the inflammatory phase. And now we actually don't have any useful antivirals. And the monoclonals can be effective, but again, you can't give them when someone's in an ICU. You have to hit them before, and we've just learned that. And these are some of the things we've talked about over the months.
Interesting. You know, I'm really interested in what you said about whether or not the spike protein was the right thing to target the vaccines, and it turns out it was very effective. Because I was having this conversation with one of my colleagues who does a lot of immunology research, and I asked the question. I like to put big questions out there to have a discussion, and the question was: do you think natural immunity or vaccinated immunity is stronger, and which one's more durable? Two different domains. And I'd love your thoughts on that. But one interesting thing he said was he thought that maybe natural immunity, if you really get sick and you mount a big antibody response, may be better because your body is developing antibodies and memory to all of the surface of the virus, not just the spike protein, and that may be better immune protection.
No, I think it's an interesting question. And there's no one answer because every virus is slightly different. For example, the human papillomavirus, the vaccines we have make amazing immunity, better than immunity you get from natural infection, because there's so much protein in those vaccines, and you end up having great mucosal immunity, which is what you need there. On the other hand, other vaccines allow infection without disease. Of course, the polio vaccines were only.
I have to bring this back because I want y'all to listen to a key point in the entire argument.
Because there's so much protein in those vaccines.
What he just said, and I'm gonna let him say it again. The key point in the vaccine that helps is that there's so much protein in the vaccine that it's safer and healthier. Let them be
Papillomavirus, the vaccines we have make amazing immunity, better than immunity you get from natural infection, because there's so much protein in those vaccines, and you end up having great mucosal immunity, which is what you need there. On the other hand, other vaccines allow infection without disease. Of course, the polio vaccines were only tested to prevent polio, not to prevent infection. That's all we cared about. Now, for SARS-CoV-2, yes, having other proteins in the mix is a good idea. I think it depends on the severity of the disease. We did a paper 6 months ago, which studied people who had died from COVID. So this was very serious disease. And their lymph nodes had no germinal centers, which means no memory B cells to SARS-CoV-2, even though they had antibodies. They had very low affinity antibodies. And so the outcome of that was the idea that if you have a very serious disease, then you're not likely to have a long memory response. Now, those are people who died, so we don't know how it applies to people who have lived, because they were able to take out their lymph nodes and study them, and it's not so easy to do in people who have survived. So a natural infection can have consequences. So on the one hand, you make a lot of viral proteins, and those are great epitopes for mainly T cells, because I think most of the antibodies that are going to block infection are going to be spike directed. But any other viral protein could, in theory, be a T cell target. So you'll get more epitopes. The counter view is that the virus may encode immune antagonists that could alter the immune response in some way that's not as good as, say, a vaccine. So it really depends, and we don't know enough yet. So I think if people are making the blanket statement that natural infection is always better, that's not always correct. It really depends on the virus.
Yeah, and it seems like we just don't have the data yet on it. If anything, it seems like the reinfection rate after natural immunity is a little higher than the infection rate after vaccinated immunity, understanding they're really two different time courses, because we've had natural immunity for a year, we've had vaccinated immunity for 6 months.
Right.
What are your thoughts on activated T cells that confer some immunity, albeit maybe partial, even when you don't have antibodies in your circulation. Because a lot of people have gotten antibodies, antibody tests, and we sort of estimated prevalence of natural immunity from seroprevalence studies using circulating antibodies. How much more immunity is out there than is being represented in those with circulating antibodies?
I think the T cell immunity is substantial and really has been ignored there. And the reason is it's very easy to look for antibodies that block infection. You do a neutralization assay with virus in the lab, and it's pretty straightforward. T cell assay, if you want to know, do infected or vaccinated people make virus specific T cells? It's harder. You have to synthesize first short peptides covering all the viral proteins. You have a company do that. They make thousands of peptides. And then you have to get lymphocytes from the patient, put them in culture. They have to be alive. And then you throw the peptides in.
It's not a commercial test, basically, right? It's not a commercial test.
Not a commercial.
It's a laboratory test.
It's a laboratory test, and it takes time and it's expensive. And so that's why it's so infrequently done. A few labs do it. But the few who have found that, first of all, as you would expect, many viral proteins can be T cell targets. And as I said earlier, the variants do not have changes in T cell epitopes because, and this is very interesting, when you are infected and you make a variant, say, that evades an antibody, that variant can go to someone else and evade their antibody too. So it spreads through the population. If you happen to make a variant that evades a T cell, it's not going to make a difference in the next person because everybody's T cell epitopes are different. And so T cell variants of viruses generally take many, many, many years to emerge. So it's not an issue. And so I think the T cell immunity, the last defense against an infection, right, to kill the infected cells, that can protect a lot of people in face of an even low antibody response. There are some A-gamma globulin-emic people who don't make antibodies who have been infected with the virus, and they don't have an unusually severe course because I think the T cells are actually protecting them.
I saw some research from Karolinska Institute that suggested maybe as many people have activated T cells and no antibodies as people who have antibodies. It's unclear how many of those people with activated T cells and no antibodies actually have immunity. But roughly speaking, how many more people have immunity, do you think, from those activated T cells than have circulating antibodies? Maybe roughly another 10%, 20%, 50%? Understanding it's partial.
Yeah, I don't know. That's a number I can't come up with, unfortunately. I do think that at some point there is a tipping point, right? So for influenza virus, T cells are also important. Yet when the virus changes in the B cell epitopes, we decide to change the vaccine, right? And so that suggests to me that antibodies do contribute. As a T cell biologist told me once, I would not want to have no antibodies. Even though my T cells are great, I still want to have some antibodies, and the two work together, right? So I don't know the number that you're asking for, though. I can't provide that.
If you don't know, I don't think anybody knows. Vincent, so
I don't know about that.
So I'm satisfied in that I've taken it up as far the ladder as I can here. In terms of antivirals, there's a promising drug, I believe it's molnupiravir, and it has been found to clear the virus in 5 days, and that was 24% better than the placebo controls in a phase 2 trial early readout. I heard there was going to be another readout. I didn't see it, but are you optimistic about that particular agent or its class of antivirals?
Right. So this is a what we call a nucleoside analog. So it's a building block for the RNA of the virus, and it inhibits the polymerase basically. And this is a great target because cells don't have such an enzyme, so it should be relatively low toxicity. I think molnupiravir is fabulous. It was shown to work really well at preventing transmission in ferrets last year. And now in the phase 2, and this is exactly the drug we need because it's orally available. You just take a pill, and at your first positive test, you could take this and probably completely alter the course of not just disease, but also shedding. But the crazy thing about molnupiravir, it was around 4 years ago. It was sat on a shelf. Nobody pushed it forward. It was a drug that was developed, and it was known to inhibit coronaviruses. And I always say, man, if we had brought that to, say, a phase 1, so that in January last year, we could have then gone into a phase 2 and 3 right away, this outbreak would have been completely different, assuming we could make enough of the drug to treat everyone, right? So, and of course, the other hand is we're going to get resistance to that drug immediately. So one drug is not enough. Nevertheless, I am very excited about it, and I just hope we have some others, because we've learned from HIV antiviral therapy, 1 drug isn't enough, 2 is not enough, 3 is the magic number that you need to treat people with.
Interesting. And would say remdesivir potentially one of those 3 in the cocktail or something like that?
My understanding is that remdesivir, even if given early, is not terribly effective. It works well in the laboratory and in blocking virus, but it's not very good in people. Plus, it's intravenously administered, so that makes it tough. And as you know, we're setting up infusion centers so that people can get remdesivir, and monoclonals more particularly, outside of the hospital. I don't think remdesivir is part of that mix. So far, we just have molnupiravir. Now, there are a lot of other drugs in the pipeline and companies have. Molnupiravir is a drug that existed before, but there are others that are being made that are purposefully selected for SARS-CoV-2. And I think it's important to push those forward in case we need to, quell outbreaks and so forth. And we need to have a few of them. If we could make them more broadly acting, would be great, right? Make an RNA inhibitor like molnupiravir that could inhibit many coronaviruses, so that when the next one comes out of bats into people, which is going to happen probably in 10, 20 years, we'll be ready to take care of that.
Do you know when the next readout of a molnupiravir trial is expected? I think they either just finished phase 2 or started phase 3.
Yeah, they finished the phase 2 a couple of weeks ago, and they said they were immediately enrolling phase 3. So I suspect they're still enrolling. And it depends where they're doing it, because some parts of the country have fewer cases than others, and so one hopes they're in areas where they're going to get the numbers more quickly, because if there are a lot of cases, they can get their phase 3 data very quickly. So I'm not expecting that, certainly before the next few months.
Hopefully in time before the fall, if there's a fall threat. It is amazing, isn't it, how the pandemic is regional in the United States. It's almost as if we're looking at different countries, when we look at Arizona versus Michigan or something like that. Anything else you'd like to add?
I would just like to assure people that vaccination is going to take care of this pandemic. There's a lot of narrative about variants and escaping vaccines. By the way, a paper just came out in Lancet showing that the UK variant B.1.1.1.7 is not more virulent as people have been claiming all along. So that's good. And I think that this is going to be shown for most of the variants. I think the vaccines will handle them for now. I think we can get out of this. So please get vaccinated, continue to be safe. And I'm suspecting that in the fall, we can get back to life as usual.
Dr. Racaniello, great to be with you. Thanks for sharing your wisdom with MetaPage today. Enjoyed talking with you and look forward to doing it again sometime.
All right, so we basically just heard from Vince Racaniello. I want to read something real quick before I get into this next bill about immunological memory, because I told y'all to remember that. Once an adaptive response has been established and the viral infection is subdued, the individual is immune to subsequent infection by the same pathogen. Immunological memory of previous infection is one of the most powerful properties of adaptive immune system and makes vaccines possible. While the primary response takes days to reach its antiviral potential, a subsequent encounter with the same pathogen awakens a mass reaction that mobilizes within hours of pathogen entry. This process occurs because a subset of viruses activated B and T lymphocytes called memory cells is maintained after each encounter with the foreign antigen. These cell populations survive for years and are ready to respond immediately to a subsequent encounter by rapid proliferation of induction of the antiviral effector functions. Now, because such a secondary response is usually stronger than the primary one, childhood infection protects adults, and immunity conferred by vaccination can last for years, sometimes for a lifetime. It is important to note that a memory response does not protect against reinfection, but rather against symptoms that arise following unrestricted infection. Consequently, an individual may be exposed repeatedly to a particular pathogen and never be aware of it, because the memory response eliminates the virus before illness appears. So I wanted to, from a non-biased perspective, I wanted to give all you natural infectionists people something to look at. And let me get to 175. I hope I'm not too blurry on the screen, but I am trying to make it visible. People with iPads and laptops. I know it's hard for people with cell phones, but I'm going to read it for you. So, like I said, all my sources are linked up and they're in the chat for anybody. Now, I just want to read the key messages here. And then I'm going to read the first statement about the objective of the scientific brief. So this is about natural immunity. Within 4 weeks following infection, 90 to 99% of individuals infected with SARS-CoV-2 virus develop detectable neutralizing antibodies. The strength and the duration of the immune response to SARS-CoV-2 are not completely understood, and currently available data suggests that it varies by age and severity of symptoms. Available scientific data suggests that in most people, immune response remain robust and protective against reinfection for at least 6 to 8 months. Let me slow that all the way down. Okay, so they're saying within 4 weeks of infection, 90 to 99% of individuals infected with SARS-CoV-2 develop detectable neutralizing antibodies. The strength and duration of the immune response to SARS-CoV-2 are not completely understood, meaning they don't know how long this immune response, the duration of this immune response lasts for you naturalists. However, scientific data suggests most people's immune responses remain robust and protective against reinfection. That means you're protected against reinfection for at least 6 to 8 months after infection. The longest follow-up for the strong scientific evidence is currently 8 months. So we know between 6 to 8 months, you got some type of immunity naturally. All right, your antibodies. We know the first 4 months, they're strongest. After 4 months, they dwindle. That's why they say 6 to 8 months, because after 4 months, you start losing them antibodies, making you more susceptible to reinfection, no matter who you are, no matter if you get some type of memory or whatever. Now, some variant SARS-CoV-2 viruses with key changes in the spike have reduced susceptibility to neutralizing antibodies in the blood. While neutralizing antibodies mainly target the spike protein, cellular immunity elicited by natural infection also target other viral proteins, which tend to be more conserved across variants than the spike protein. The ability of emerging virus variants of interest and variants of concern to evade immune response is under investigation by researchers around the world. So there's a lot of unknown naturally, right? And we've already determined that a natural infection takes longer to create antibodies. We know this because the data says within 4 weeks. We know it's 2 weeks with the vaccine. And it's a lot safer, less riskier, and you don't get sick. So you have to get sick and you have to get infected, get sick, and go through a whole little sickness process before you can develop any antibodies with the natural way. The safer way is with a vaccine. Now, there are many available serologic assays that measure the antibody response to SARS-CoV-2 infection, but at the present time, the correlates of protection are not well understood. So they had a scientific briefing about this immunity passports and all of that stuff that was published. I ain't trying to get into none of that. COVID-19 immune response to natural infection. This study right here goes through the whole process. It even talks about reinfection. And they say thoroughly reported to date, reinfection with SARS-CoV-2 can occur. So for all y'all think it can't happen, it can occur. 4 large studies from the UK, the US, and Denmark estimated that infections with SARS-CoV-2 provided 80 to 90% protection from reinfection up to 7 months and up to 94% protection against symptomatic disease. The level of protection against reinfection and assessed by PCR positivity was estimated by 50% in people aged over 65. All right, so measuring immune responses, they have all of this. I don't even want to go through here, but I can read you the conclusion. Current evidence points to most individuals developing strong protective immune response following natural infection with SARS-CoV-2. However, inaccurate immunodiagnostic tests may falsely indicate infected individuals as naive to the virus, not previously infected, or may falsely label non-infected people as positive for immune markers of recent infection. To conclude, available tests and current knowledge do not tell us about the duration of immunity and protection against reinfection. But recent evidence suggests that natural infection may provide similar protection against symptomatic disease as vaccination, at least for the available follow-up period. The emergence of variants of concern poses challenges and their potential to evade immunity elicited by natural infection or by vaccination needs to be closely monitored. Now, remember, this was published by who? On May 10th. The information that I provided you in the beginning of the argument was after this. So we had updated science that followed up the WHO doc. All right, so I'm gonna lay it on you real quick, but not all the way. Is it better to get immunity from catching COVID or vaccines? What science shows? So this article here is 5 minutes. I'm gonna play the audio. I'm not gonna read it for 5 minutes.
Is it better to get immunity from catching COVID or vaccines? What science shows? Research shows both coronavirus infection and vaccination offers immunity that can protect people from getting sick again. But by how much and for how long remains unclear, a scientific gap that only time could fill. Regardless of how immunity is acquired, there's no telling whose bodies will or won't create effective antibodies, and why they last longer for some than others. Doctors speculate age or certain medical conditions might play a role. It also doesn't help that the testing shortage that plagued the nation at the beginning of the pandemic will forever shield researchers from understanding the true impact of COVID-19. The Centers for Disease Control and Prevention estimates that between February 2020 and March 2021, there were about 114.6 million total coronavirus infections in the US. That's about 81.1 million more cases than are confirmed as of June 17. While people can gain immunity from both infection and vaccination, antibodies created from both routes target different parts of the virus, which leads to variations in the quality of protection. It's like a coin flip: risk contracting COVID-19 and potentially becoming a long hauler, or getting vaccinated. Some argue the final outcome is similar, but one is far more dangerous than the other.
Expedia knows what happens when you travel.
Jeez. I apologize for that. I'll mute this thing when the commercial last stop. Jeez. It's killing us. Knowing I hate that. We got 6 seconds. 4, 3, 2, 1.
It's what the latest data show about immunity from prior infection and vaccines. Natural immunity from coronavirus infection. There are certain illnesses in which infection can offer more protection than a vaccine. For example, coming down with measles or mumps is said to confer lifelong immunity to the virus, but some people who get the vaccine may still get infected, although the shots still limit and prevent the spread of outbreaks. But if the novel coronavirus is anything like others in the coronavirus family, like the Middle East Respiratory Syndrome, MERS, then permanent protection after infection is unlikely. Studies offer some positive clues, however. Research published in February found that coronavirus patients gained substantial immune memory that involved all four major parts of the immune system: memory B cells, antibodies, memory CD4 plus T cells, and memory CD8 plus T cells. This protection lasted about 6 months after infection in most people, but for some, it remained for up to 8 months, suggesting it could last even longer in some cases. Separate research posted in April showed a history of COVID-19 among UK patients was associated with an 84% lower risk of reinfection for about 7 months after testing positive. Another non-peer-reviewed study published in June found that over 5 months, 1,359 American healthcare workers who previously had COVID-19 and didn't get vaccinated stayed clear of reinfection. The Cleveland Clinic researchers said, in the context of a short supply of vaccines globally, a practical and useful message would be to consider symptomatic COVID-19 to be as good as having received a vaccine, adding that people who've had the coronavirus are unlikely to benefit from COVID-19 vaccination. While scientists cannot predict who will develop natural immunity, evidence shows people who had severe COVID-19 are more likely to develop a stronger immune response than those who had milder forms of the disease. Immunity from COVID-19 vaccines. It's also true that research shows COVID-19 vaccines offer protection against reinfection, although breakthrough cases can occur because no vaccine is 100% effective. However, studies have found vaccine-derived antibodies are more robust compared to those from natural infection, and the job is done without causing illness or other long-term complications often brought on by the disease. 2 doctors from Italy compared the process of infection and vaccination in relation to variants to the plot of an action movie. It begins with a character, the virus, running freely across the globe, eluding capture until being finally sent to jail, built by natural immunity. However, if this prison is not secure enough, the virus could escape, aided by certain mutations. Dr. Emanuele Andrino and Dr. Rino Rapoli of the Monoclonal Antibody Discovery Lab wrote in Nature, vaccine-induced immunity should help ensure those escape routes are securely closed. An April study that has not been peer-reviewed found that 2 doses of either the Pfizer or Moderna vaccines offered 10 times higher levels of antibodies compared to those developed after natural infection. Another April paper showed that people who were previously infected with the coronavirus experienced significant boosts in their pre-existing antibodies after 2 doses of the Pfizer vaccine, which also offered protection against coronavirus variants. Vaccines actually, at least with regard to SARS-CoV-2, can do better than nature. They are better than the traditional response you get from natural infection, White House Chief Medical Advisor Dr. Anthony Fauci said during a COVID-19 briefing in May. Exactly why vaccines appear to generate more robust immunity than natural infection remains unclear, but Dr. Sabra Klein, a virologist and professor of immunology at Johns Hopkins Bloomberg School of Public Health, said infection and vaccination work in different ways. The immune system of people who have been infected has been trained to target all these different parts of the virus called antigens. You'd think that would provide the strongest immunity, but it doesn't, Klein said. The Pfizer or Moderna vaccines target just the spike protein, the part of the virus that is essential for invading cells. It's like a big red button sitting on the surface of the virus. It's really sticking out there, and it's what our immune system sees most easily, she continued. By focusing on this one big antigen, it's like you're making our immune system put blinders on and only be able to see that one piece of the virus. In other words, vaccines work to strengthen immune responses gained during natural infection. That's why health experts advise people who have had COVID-19 to still get vaccinated. There's nothing deleterious about getting a boost to an immune response that you've had before, Dr. Marion Pepper, an immunologist at the University of Washington in Seattle, told the New York Times. You could get an actually even better immune response by boosting whatever immunity you had from the first infection by a vaccine.
Next article.
There you go.
Federal judge throws out CDC's cruise safety
Y'all for real gonna try to do that? All right, so that was one article. Now, y'all know I'm loaded up, but I'm not going to go through everything. But this pretty much, I had to deal with a claim and then a debunking of a claim. So the claim was made by this guy right here we're going to talk about. So, now, COVID-19 vaccines cause over 4,000 deaths. COVID-19 survivors can't get the virus and don't need to be vaccinated. Natural immunity trumps vaccine immunity. Spike protein from the vaccines is dangerous. Okay, the verdict was inaccurate, of course, but Cases of reinfection of COVID-19 survivors were documented. Therefore, it's false to claim that COVID-19 survivors can't get the virus again. Phase 3 clinical trials of COVID-19 vaccinations authorized the U.S. Food and Drug Administration, FDA, which it says safety and efficacy, and tens of thousands of volunteers have been running for about 4 to 5 months before authorization was granted. While infection tends to grant better immunity than vaccinations most of the time, that they're claiming this is misleading. So getting the diseases associated with a higher risk of death and health complication, vaccines generate immunity in people while avoiding the risk associated with the disease itself. So yeah, I want to throw this in because, you know, Peter McCullough, who's a cardiologist, made the assessment claim, right? Without any substantial proof, he just made the claim. And of course, like all claimants, they're going to blame theirs. And the truth of the matter is this: McCullough didn't cite his source when stating his figures, but the ballpark figure of 4,000 has been cited before in another claim on COVID-19 vaccines. It corresponds to the number of reports of deaths occurring on COVID-19 vaccines in VAERS. VAERS collects reports of adverse events that occur after vaccination. Its purpose is to serve as a surveillance system that allows public health authorities to detect signals that may indicate potential safety problems. However, VAERS reports have provided fertile ground for COVID-19 vaccine misinformation. This is where a lot of the misinformation comes from, because they are disingenuously misrepresenting VAERS and then don't tell people that this is just a reporting system. These are not confirmed incidences. Next, and I'm about to wind it on down for y'all, but of course, SARS-CoV-2 immunity persists for up to 11 months after natural infection. Y'all heard me talking about this earlier. In summary, the Journal of Nature published an article talking about how long the antibodies last and or persist to. They say 11 months because you could, if you do a PCR testing or whatnot, there will be some signs of some type of antibodies, but it just will not be as strong as it was in the first 3 months of testing, which means that after month 4, your antibodies begin to dwindle. After month 7, they slow down. 7, 8, 9, 10, and around the 11th month period, they just become noticeable. So I'm really not going to read too much of this particular article because I've beat that with a dead horse through the whole conversation. But I just wanted to have that in there for people who might want to know. All right, now this is another one that talks about the natural immunity or acquired from SARS-CoV-2 for up to 11 months, as the other source says, but this is more direct, right? And this follows up, or this goes with it. Now, you know, you can get the PDF and go through all of that and, you know, get your sources here, but this pretty much is an abstract of some stuff that was found out. Excuse me, I had to yawn. But anyway, yeah, so natural immunity, they have a time step on it, up to 11 months. It's really not, it's between 6 to 8 months. They have seen people get tested and have some type of antibody response, but it's very, very limited. It's not as strong as they thought it would be. So this whole notion of long-lasting immunity is a figment of one's imagination. So moral of the story in closing, natural immunity is not the way to go. It is not the way to go. Why is it not the way to go? Because we just proved the case. Natural immunity, you risk infection. You have to be sick, and you have to go through a process before you can even develop any type of antibodies. The vaccine is safer. You don't have to go through all those sicknesses, and it creates antibodies a lot quicker. Remember, we need to understand the immune system, those 3 things: adaptive, passive, and innate. Innate, adaptive, and passive. We need to understand those things because with vaccine science, those three are intricate pieces. And these are the things, though, not understanding the immune system can cause Facebook arguments to continue and continue and continue because people are going to misrepresent the data and they don't understand what the immune system is or how the immune system works. And they don't understand that natural infection has way more complications than vaccine does. So in closing, for those of you who are literate enough to understand, natural immunity is more harmful and can kill you potentially or go a long way and cause other issues. And vaccine immunity is safer. It's a better way to protect yourself. And you heard a virologist, Vincent Racaniello, say that because of the proteins in the vaccines, that is a great way to go. The protein in that whole process creates a more robust protection than a natural infection. All right, so I am going to end. I'm gonna say Shimim Hotep to everybody on the Mossy Warrior Clan YouTube channel. This concludes the actual bill. As you can see, Brother Sutek in the chair talking about we about to go over on Science with Shawn, because that's where the rest of the conversation is being had. So I'm going to stop the Mossy Warrior Clan now, and then I'm gonna build with the brothers and sisters in the chat on Science with Shawn. So the link is in the chat to join us on Science with Shawn if you're interested in continuing the build. Other than that, Shimon Hotep to everybody on the Mossy Warrior Clan side.